Welcome to the debate. So, imagine a massive, state-of-the-art factory designed to build the world's fastest cars. The machines inside are incredibly efficient.
Mm-hmm.
They can optimize the engine timing, they can tweak the aerodynamic profile, they can even test new tire compounds. But the factory has a fatal flaw.
Right. The machinery of improvement is completely locked in place. I mean, if you suddenly realize you need to build airplanes instead of cars, the entire assembly line freezes up.
Exactly.
The factory just can't redesign its own floor plan. It lacks the capacity to step outside its predefined parameters.
And for decades, well, that has been the exact bottleneck in artificial intelligence. If you want an AI to get smarter, human engineers have to manually rewrite the code that makes it smarter.
Which is incredibly slow.
Very slow. But what happens when the AI writes the code that improves its own brain? Today, we are exploring the emergence of self-improving AI architectures. Specifically, we're focusing on a 2026 framework known as HyperAgents and the Darwin-Gödel machine with HyperAgents, or DGMH.
Yeah, so the central question we are unpacking today is whether this DGMH architecture represents a genuine paradigm shift toward unbounded, open-ended AI self-improvement, or, if it is fundamentally just a highly constrained optimization loop relying on fixed models and simulated environments.
Right. And I will be arguing that by giving the system the ability to edit its own underlying improvement mechanism, this architecture breaks that historical bottleneck. It enables true cross-domain intelligence.
And I will argue that while the system demonstrates incredibly impressive engineering, it remains bounded by human-designed rules and perfectly structured sandboxes. It falls well short of truly open-ended self-acceleration.
Okay, so to set the stage for our listeners, we need to understand the infinite regress problem. It's a classic philosophical and structural trap in computer science.
Oh, absolutely.
If you build an AI system and you want to automate its improvement, you build a meta-system to oversee it. But then, who improves the meta-system?
A meta-meta system.
Exactly. A meta-meta system, it's turtles all the way down. Somewhere at the top, a human being has to hard code the final rules of how the system learns.
Which means the system can never outgrow the imagination of the human who wrote those final rules.
Precisely. And previous systems, like the original Darwin-Gödel machine, were strictly bounded by this. In software engineering tasks, the original DGM worked brilliantly.
Because evaluating code and writing code use the exact same fundamental skills.
Right. It could use its coding ability to write better coding tests. But this alignment fails the moment you step outside of software. So, by unifying the task agent, the part doing the work, and the meta agent, the part evaluating the work, into a single editable Python program, DGMH enables what researchers call metacognitive self-modification.
It's a very elegant bypass of a structural friction point, I'll give you that. Combining them into one script means the system can technically edit any part of itself.
And that breaks the infinite regress. It doesn't just learn to solve a new task. It rewrites the very mechanism it uses to generate future improvements. We are witnessing the first sparks of a system that improves its own ability to improve.
Well, I come at it from a different way.
Okay.
I certainly acknowledge the clever engineering involved, but the theoretical implications drawn from this are vastly overstated. I assert that what we are looking at is still a highly constrained optimization search.
A search?
Yes, it is not unbounded, open-ended intelligence.
But how can you say it's constrained when it's literally rewriting its own source code?
Because we have to look at what is actually doing the thinking. The DGMH system fundamentally relies on a frozen foundation model for its core cognitive capabilities.
Which is important to clarify for anyone listening who might not be familiar with that term. When you say frozen foundation model, you mean the underlying neural network, like the massive AI models we use every day, has its weights locked.
Right.
It isn't actively learning or changing its internal brain structure during these tasks.
Exactly. The brain is static. The DGMH is essentially an algorithmic wrapper around that static brain. It's just writing Python scripts to ask the brain better questions.
A wrapper is a bit dismissive, don't you think?
Well, furthermore, it requires highly structured simulators to function. To claim it is redesigning the factory floor ignores the fact that the evolutionary rules of this system, specifically the parent selection mechanism that decides which versions of the AI get to survive and reproduce, remain fixed, human-crafted heuristics.
Right, but
Therefore, the system is simply finding clever ways to optimize Python boilerplate within a tightly controlled sandbox, not escaping the boundaries of its initial human design.
I'm not convinced by that line of reasoning because you are dismissing the structural architecture as mere boilerplate. Let's look at the transition from the original DGM to the DGM-H, because the mechanism of action here is where the breakthrough resides. Let's take the paper review task from the source material.
A fascinating domain to test this on, yeah. The AI has to read a full machine learning research paper and predict a binary accept or reject decision, mirroring human peer review.
Right, and when the researchers took the original DGM and applied it to this paper review task, it completely failed. It scored a flat 0.0 without human customization.
True.
It simply didn't have the internal tools to optimize for a domain that wasn't strictly code generation. But DGM-H, because it can rewrite its own meta agent, successfully self-improved to a 0.710 score.
Right.
It actually outperformed the state-of-the-art baseline, which sat at 0.630. That is a massive leap.
That's a compelling argument, but have you considered the nuances of that 0.0 starting score?
The initial agent failed the paper review task simply because it lacked formatting post-processing.
What do you mean by that?
The evaluation environment, like the testing software grading the AI, required a very specific output format to register a decision. The original DGM didn't provide that exact parsing.
Ah, the formatting. Right. It didn't output the text in the exact way the grader wanted. It scored 0, not necessarily because it lacked deep reasoning about the papers, but because it didn't write the script to extract its own conclusions properly.
So you're arguing the intelligence was already there, it just couldn't fill out the paperwork.
Precisely. So when we see the GGM-H go from 0.0 to 0.710, what are we actually witnessing?
Actual improvement?
No. I argue that this largely reflects the meta-agent learning to write better Python boilerplate. It learns to write multi-stage checklists. It writes explicit evaluation pipelines.
Okay.
It is writing code to better extract the frozen foundation model's pre-existing knowledge. It is not generating fundamentally new cognitive capabilities.
I disagree.
The actual comprehension of the machine learning papers resides entirely in the frozen LLM making the API calls. The Python wrapper just got better at formatting the prompt.
I see why you think that, but let me give you a different perspective. A checklist isn't just formatting if the system didn't have the capacity to explicitly follow steps before.
But it's just steps.
The checklist and decision rules the DGM-H wrote for itself were novel structured evaluation pipelines that fundamentally changed how the foundation model approached the problem. The system shifted from superficial instructions, like telling the model to adopt a rigorous persona, to explicitly defined criteria and decision trees.
Yeah,
That is a novel cognitive architecture.
it's a novel prompting strategy.
But let us look at the transferability of these architectures, which directly counters the idea that it's just local text formatting.
Okay, let's look at it.
If you're listening to this and wondering why writing a checklist for a paper review matters, consider what happens when the AI takes that skill into an entirely different domain. Look at the Olympiad math grading experiments.
Right, the IMO grading bench.
Right. This is a held-out evaluation. The researchers took HyperAgents that have been optimized in entirely different domains, specifically robotics and paper review, and transferred them to this math grading task. And those HyperAgents successfully transferred their meta-level improvements. They autonomously wrote a performance tracker class in Python.
Which is a very common structure.
Yes, but they built a system to track their own metrics across generations, saving historical data to a JSON file to inform future modifications. If the system is merely writing formatting boilerplate, how do you explain its ability to invent persistent memory tracking that accelerates its learning in a domain it has never seen before?
I'm sorry, but I just don't buy that it invented memory. Let me tell you why. We have to look at the environment itself.
Go on.
Writing a performance tracker class to save data to a JSON file is a ubiquitous software engineering solution. It's standard practice.
But the AI implemented it autonomously.
Because the HyperAgent is operating in a Turing-complete Python environment. It has access to every programming tool imaginable, and it has the vast software engineering knowledge embedded within its frozen foundation model.
Sure.
It is simply applying standard programming patterns to solve search space problems. It isn't inventing persistent memory from scratch like some emergent biological trait. It is retrieving a highly probable Python scripting pattern to manage data over time.
Okay, but even if it's retrieving a known pattern, the fact that it recognizes when and why to apply that pattern to improve its own meta-learning process is a massive leap.
It's impressive automation, yes. But when you emphasize transferability, we have to look critically at the domains themselves. Let's talk about the robotics task.
The robotics reward design task. This is where it gets really interesting, because we're moving from text processing to physics.
Right.
The goal was for the AI to write a reward function, basically a set of mathematical incentives, that would teach a simulated quadruped robot how to jump.
And yes, the DJMH generated a reward function that taught the robot to jump, scoring 0.372 versus the baseline of 0.348.
A clear win.
But we have to explain how it was able to do so. It was operating against a perfect, frictionless physics simulator. Frictionless in the sense of data, not actual physics, right?
Correct. The simulator provided immediate mathematically pure feedback on every single generated code iteration.
Right. The AI tries a line of code, the simulated robot falls over, the simulator instantly returns a precise error score.
The DSDNH thrives because the sandbox is perfectly designed to return clean error messages and objective fitness scores.
Which is how you train it.
But that is a far cry from the messy, ambiguous reality of open-ended scientific discovery. You can't just run a billion rapid-fire physics simulations in the real world when you're trying to discover a new drug or invent a new material. That's an interesting point, though I would frame it differently. The importance isn't just that it succeeded in a simulator, it is how it succeeded.
Okay.
And this goes directly to your point about the system being trapped in a sandbox. The initial agent generated reward functions that completely failed.
Right.
Over time, the DGMH incrementally built an internal knowledge base. It mapped out environment constraints, identified valid state variables, and developed reward scaling heuristics. But more importantly, it escaped a highly attractive local optimum.
The standing tall trap.
Exactly. For our listeners, a local optimum is a trap where the AI finds a solution that is good enough and stops looking for a better one, because any slight change makes the score worse before it gets better.
Right.
In this robotics task, the default reward function optimized for torso height. The easiest way to get the torso high is to just make the robot stand straight up and lock its knees.
Which is not jumping. But jumping requires bending the knees first, which lowers the torso, which temporarily lowers the score.
Yes, it requires taking a step backward to take 2 steps forward. The original DGM, even when manually customized for the domain, often generated task agents that failed to escape that standing tall trap.
When it couldn't conceptualize the temporary loss of score.
Right. DGMH, however, successfully avoided premature convergence and discovered jumping. It re-engineered its own search parameters to explore a completely different behavioral space. And it did this while simultaneously running paper review tasks in the same experiment run. It was jointly optimizing for entirely disparate tasks.
Look, I don't dispute the empirical gains. When the researchers ran what's called an ablation study, basically stripping away the AI's ability to look at its past experiments and self-improve, its performance completely flatlined.
Right, so it needs that history.
It requires that metacognitive loop to build up domain knowledge over time. The archive of previous agents acts as a vital stepping stone, preventing the system from getting stuck.
So you agree the open-ended exploration works?
The archive works, but this brings me to my most structural critique. This is the illusion of true open-endedness. The archive works, but the rules governing the archive are static.
Explain what you mean by the rules governing the archive.
In this system, there is a parent selection mechanism. It's the algorithm that decides which hyperagent from the archive gets to self-modify and produce offspring for the next generation.
Right.
That mechanism is fixed. It is probabilistic, weighted by past performance,
and inversely proportional to the number of successfully compiled children.
Which prevents the system from just relying on the same successful script over and over again. It forces diversity.
Yes, but it is a human rule. Because this evolutionary selection pressure is fixed and human-designed, the system is trapped in a fitness landscape created entirely by the researchers.
I see.
It cannot change what it values. It cannot redefine what constitutes a good agent beyond the metrics provided by the human engineers. Therefore, it is still playing a game designed by humans. It is navigating a maze incredibly fast, but it cannot redraw the walls of the maze.
I see why you think that, but let's look closely at the source material. The researchers explicitly state that in principle, a fully self-referential algorithm allows modification of every part of itself, including that parent selection mechanism.
But they didn't do that.
They kept the parent selection mechanism handcrafted and fixed in these primary experiments, specifically to isolate the effects of the HyperAgent self-modification.
A control variable.
Exactly. In science, you need a control variable. They needed to prove that the task and meta-agent were actually driving the progress, rather than just chaotic mutations in the selection rules. But the architecture itself is not structurally locked into that heuristic.
Even so,
The task agent and the meta-agent are fully editable. They are just code.
but again, relying on a frozen foundation model.
That is not the limitation you suggest. You argue that the intelligence is frozen in the neural network weights. But think about humans.
Humans?
Yeah, human intelligence operates on frozen biological hardware. Our actual neural architecture hasn't fundamentally changed in thousands of years.
Well, I mean, that's...
What changes is our software, the cognitive frameworks, the scientific methods, the mathematical tools we invent and pass down. The DGMH is inventing its own cognitive software.
Right.
When it writes a multi-stage checklist or a persistent memory class, it is creating new conceptual tools that allow its frozen foundation model to achieve outcomes it could never reach on its own.
I'm sorry, but the biological hardware analogy completely breaks down there.
Why? We use the same brain to invent the wheel as we do to invent the microprocessor.
Because human brains are capable of paradigm-shifting conceptual leaps for one specific reason. We interact with an unbounded physical reality.
Okay.
We encounter novel friction that forces fundamental reconceptualization. The DJMH is interacting with an LLM prompt interface and a Python compiler. You say the architecture isn't structurally locked, but the system's entire feedback loop requires a computable task with an objective evaluation metric.
Meaning it needs a clear score to know if it did well.
Exactly. In paper review, it relies on a validation subset of human decisions to know if its checklists are right. In coding, it requires test cases.
Sure.
In robotics, it requires the simulator's physics engine to tell it if the robot fell over. Without an external, human-provided oracle grading its every move, the meta-agent has no compass.
Right.
It cannot autonomously discover new fields of science because it cannot evaluate the truth value of a novel discovery without a predefined reward function.
So without a teacher giving it a grade, it doesn't know what to learn.
Precisely. It is a brilliant automated software engineer. It is an evolutionary algorithm that optimizes prompt engineering and Python script generation to an unprecedented degree. But it is not open-ended intelligence. It is bounded by the necessity of immediate, computable evaluation. If you put a HyperAgent in a sandbox, it will build the most magnificent, structurally sound sandcastle possible. It will invent new tools to pack the sand tighter and stack it higher. But because it doesn't experience reality outside the sandbox, it will never look up and decide to build a skyscraper out of steel.
That's a great metaphor, but I think you're underestimating how much of reality we can now put into the sandbox.
Oh.
I concede that the system currently requires computable tasks to evaluate its self-modifications. However, the scope of computable tasks is vastly broader than you are implying. Science itself is increasingly becoming a computable task.
In what sense?
We simulate protein folding. We simulate fluid dynamics for aerospace engineering. We simulate quantum chemistry. If a HyperAgent can optimize its own meta-level mechanism for searching a robotics physics engine, there is no theoretical barrier preventing it from doing the same in a chemical simulator or a genomics database.
I see.
The breakthrough of the DGMH is that we no longer have to manually design the search algorithm for each of those new domains.
You're saying the AI will build its own map of the territory?
Write its own performance trackers, its own parsing logic, its own memory management systems.
Mm-hmm.
It is autonomously evolving the meta mechanisms of discovery. And as the source material shows, these self-improvements compound. They accumulate across runs. An improvement in memory management learned while grading math Olympiad problems can be applied to designing robotic reward functions.
Right.
That compounding, cross-domain metacognition is the definition of a paradigm shift.
Well, I will certainly acknowledge that the compounding is impressive. When the meta-level improvements transfer from paper review and robotics over to Olympiad math grading, it undeniably proves the system is generalizing its software engineering tactics.
Exactly.
We absolutely have shared convergence there. Integrating task and meta-level modification into a single editable Python program yields incredible empirical gains over static baselines like the original DGM.
It prevents the system from getting stuck.
It prevents it from getting stuck in local optimas as frequently, yes. But we must be careful not to conflate highly effective cross-domain optimization with self-accelerating unbounded progress.
Fair enough.
Returning to our analogies, we are looking at an incredibly efficient system for iterating on known concepts. But it still relies on frozen foundational models for its worldview, fixed evolutionary selection pressures for its motivation, and perfectly structured simulators for its reality check.
Well, let's summarize our positions in light of this discussion. From my perspective, DGM HyperAgents represent a vital, undeniable step toward autonomously accelerating scientific progress.
Okay.
By unifying the task and meta-agents, we have solved the alignment bottleneck that plagued earlier self-improving systems. We have moved beyond systems that just learn how to solve a single task to systems that actively learn and rewrite the mechanics of how to improve themselves.
Right.
They are inventing their own cognitive architecture, transferring memory systems and evaluation pipelines across entirely unrelated domains. This proves the system is no longer constrained by human imagination regarding how a problem should be solved.
And to summarize my stance, while hyperagents are undeniably a powerful structural innovation for automating software engineering around foundation models, true, unbounded open-endedness remains elusive. The architecture elegantly manages code generation and prevents stagnation, but it is ultimately bounded.
Right.
Its reliance on frozen foundation models means its underlying reasoning capacity is capped. Its reliance on fixed, human-designed parent selection mechanisms means its evolutionary trajectory is predetermined. It is a highly effective optimization loop, playing a game entirely designed, refereed, and constrained by humans.
Both of us agree that the empirical data is striking. The ability of a single script to edit its own source code to become better at reviewing machine learning papers and then carry those internal software upgrades over to an entirely different domain like grading Olympiad mathematics is a milestone.
Absolutely.
The tension lies entirely in how we measure the ceiling of this architecture.
Precisely. It comes down to the complexity of measuring true open-ended intelligence. Is algorithmic self-modification within a Python environment enough to spark runaway acceleration, or will the system eventually hit the hard ceiling of its static foundation model and simulated environments? It's the difference between learning to play a game perfectly and inventing a new game entirely.
That is the frontier we leave our listeners to consider. We encourage you to explore the source material further to decide for yourself whether this is the spark of unbounded AI or just a highly effective optimization loop. Going back to our factory, if the machine can finally redesign the factory floor to build whatever it wants, what happens when it realizes it doesn't need a factory at all? Thank you for joining us on The Debate.